Um, Hello everyone. So I will give example how to use MCPWM from ESP32 for controlling a passive full bridge converter. So this is uh, the general diagram of the MCPWM ESP32. So but maybe we can go back. I mean we can go to the circuit first. So this is the general circuit of the passive full bridge converter. So you have full bridge on the left side. Um, in usual full bridge, the duty ratio will be changed uh, depends on the load. But for the passive, the duty ratio is constant at 50% for all of the switch, but the phase between the leading leg and then the lagging leg that change over time. Because of this concept, uh, we can achieve a soft switching, especially zero voltage switching by functioning the leakage currents of the transformer or uh, adding some uh, leakage inductance to charge and discharge between for each switching. So yeah, you need to remember that in here the duty ratio is constant at 50%, but the phase that changes. So to achieve uh, this change of pace between leading and lagging leg, in here I will use my approach is by functioning the daytime. So uh, on the ESP32, the MCPWM peripheral have two groups. For each group have three timer. For each timer have three operators, and for each operator have two comparator, two generator, one dead time. So it means that for each operator you can generate two uh, two PWM signal. In here, they gave example PWM A and PWM B. Um, the my approach is by using daytime. It means that I need to adding delay on the rising edge or the positive, and adding delay on the falling edge. So the waveform can shift from zero phase to the 180 degree. So I will explain it a bit in here. Because each operator only have one dead time, it means that you can only apply uh, both positive or negative delay. It means rising and falling edge delay, both of them to only one PWM. Like in this example, if you apply both of them to PWMA, it means that you cannot apply to the PWMB. Or another case is you can apply rising edge delay or positive delay to PWMA, and for PWMB you can only add negative delay or falling edge delay. So like that. So for this I will use three operator. So one operator have two output. I mean for the leading leg, because they didn't need phase shift, so they will on the 0 degree phase shift. So I can apply only positive delay on PWMA or the Q1, and negative delay on the PWMB or the Q2. So maybe this will be a little bit clear. So yeah, like this. So I will have three operator on on the array 0, 1, and 2. So the first operator will be have two generators on array 0, location 0 and 1 for, so 0, the first generator on for Q1, and generator the second generator for Q2, and then so this is from operator on the from the first operator, and for the second operator, which is this one, will be controlling the third generator that controlling the Q3, and then say and then the last operator, the third operator, will be controlling generator on the array location 3 for Q4. It means that like this, because Q1 and Q2 didn't need both of delay on the switch, for each switch we can just using one operator. So I will apply rising edge delay to Q1, and then falling edge delay to the Q2. Because the Q2 is invert, the waveform is invert, so it means that the negative delay on Q2 will be same as the positive delay. Yeah, you can imagine or thinking about that. But for the Q3 and Q4, because I need to adding both of the delay, positive delay and negative delay, to change the phase. So I need a whole operator for only one generator, same as for the Q4. So maybe we can see on the in here. So this is from the documentation. We can see that this due to the hardware limitation, only one delay module that cannot be applied to multiple MCPWM generator at the same time. So like this. Yeah, you can read more about this. So we go direct to the program. So on the program from beginning, oh yeah, I forgot to tell you that wait a moment. Yeah, I forgot to tell you that, so I have the circuit in here. I have the circuit for phase shift full bridge. So this is this is part of my research. So in here I have Q1, Q2, and Q3 and Q4 in here. So this board is actually consists of two boards. On the top it's for the high voltage signal, the large signal, and then the bottom for the small signal for the control. So for each MOSFET in here, the control signal is isolated by isolated DC-DC converter for the supply, and then for the driver. In here, so Q1, Q2, Q3, and Q4, I have oscilloscope connected to its gate. Because I have two, I will change one at a time. So please remember that in here I only turn on the power for the control signal and then the gate signal. So it doesn't have it doesn't have the high voltage signal. High voltage line. It doesn't turn on. because my oscilloscope uh, is not isolated for the ground. So if you have a high voltage between the switch that flow, it means that when you connect for its uh, gate and source of its MOSFET, you can short circuit through your oscilloscope and fry your oscilloscope. So in here I just show the signal. Okay, so we back to the program. So Q1 on the pin 16, Q2, Q3 and Q4 as you can see from here. And for I will tell about this later. So this is we can skip this first. So for the declaration of the PWM, you can see my another video. I already explained about that. So in here we have 3 operator and 4 generator, and then you can see directly to here. You need to configure of each generator. So all of them will be start from timer when 0, and then start from timer when 0 it will be high, and then when the timer is equal the comparator, it will be on the 0 state signal or low. But in the phase shift we need have complementary signal for leading leg and the lagging leg. So for the complementary, I will using the dead time. So in the dead time, you can invert the output signal by using this flag invert output. So in here, at first, I configure for the Q1, and then for the leading leg, this is the top side switch, and then this is for the bottom side switch. So I invert the bottom side switch signal, so both of them can have a complementary signal. And then this is for the lagging leg for Q3 and Q4. So in here, for this signal to be work, you need to adding some dead time. If you put 0 in here like this, this will be not work. They just, it means I don't know, the compiler will see that, oh, we don't change anything to this signal, so they will skip this even though we put true, but the signal will be not invert. So we need to adding some delay. So yeah, like previous, I will put positive H delay for the top side or Q1, and then negative H delay for the Q2 or the bottom side. But because it's invert, then this negative delay will be have the same meaning as the positive H delay. You can think about it more detail. So so this is for the leading leg, and then this is for the lagging leg. For the lagging leg, because we need to shift both of the positive delay and the negative delay, we adding the same value of delay for two, I mean for both of them. So we can shifting the phase same as the for the bottom side. The difference is to have the same delay when the phase is 0 degree between leading and lagging leg, it means that when the it means that when this is 0, we need to have same value positive delay as this one. Similarly for this one too, like that. So we can see the waveform. So this is Q1 and Q2 signal. So it is inverted and is correct. So this is as we want. So let's check for Q3 and Q4. Let me change it to Q3 and Q4. So Q3 should be connected to here, and then this one. Let's check for the Q3 and Q4. So Q3 and Q4 complementary too. So the signal is correct. Right now we check the Q1 and Q3. It should be have the same phase right now because I put on 0 degree phase. So okay, so the yellow is Q1 and then the blue is Q3. So both of them have a 0 degree phase. Okay, let's focus on this configuration. So the yellow will be Q1 and the blue will be Q3, and we will change the phase. So we change the phase by adding delay in here. I already make some variable delay add in here. So the maximum dead time or delay in here depends on your periodics, because this is have 50% duty ratio. From beginning I put the periodics is half of the full periodics to achieve 50%. So it means that 800. So this 800 will be the maximum value for total delay. So when you put 800 in here, it means that you will have 180 degree delay phase shift. Same as if you put 0 in here, it will be 0 degree. So we can change this variable, maybe like 400. It means that will be half of the phase shift, so it will be around 90%. So we 90 degree. So we build. Just wait a while. And refresh. Okay, so as you can see that the waveform, the signal is shifting 90 degree. So this is Q1 and Q3. So leading leg and the lagging leg. So we can change maybe like nearer the maximum. Oh yeah, I try like the total will be 800, but when total delay is same as the comparator, it will be not work. So you need like lowering. It should be lower than 800, maybe like 799 or 790. to achieve 180 degree. So I will put like 780 in here. It means that I will have like 790 ticks to achieve around 180 degree. So we build. Replace, and yeah, you can see that right now it shifting almost 180 degree. Okay, so you know how to adding phase shift using ESP32. So I will give a little more example. So in here I will using the callbacks or interrupt from the MCPWM to update the dead time. So because if you want to apply this concept using a feedback, it means that the phase shift will be changed every switching. So so this is to call the interrupt function when the timer is starting from empty or zero. So we going to the interrupt function. So this is the function that will be called every uh, empty timer or zero timer. In here I try uh, to divide the the calling of interrupt like every 1000 uh, timer, because for every for so for every 1000 it will be calling, will be updating the daytime once or adding, because my frequency is my switching frequency around 100 kilohertz. So it means it will be updating every 100. So the frequency updating is around 100 hertz. So in here I will increase the phase shift, and when it's full it starts again from zero. So yeah, just as simple as that. We can start this maybe from zero, and we build. Yeah, right now you can see that uh, the blue waveform is moving or shifting. So yeah, it will be start from zero, and when full it start again from zero. You can apply this concept for applying some feedback to this converter. So yeah, that's all from me. I hope you can understand what I want to explain, because I don't have any preparing at all. So yeah, sometimes my explanation will be a little bit confusing. So thank you for watching.